So today I'm trying something different. I have this nice setup at the math department and we'll see if it works. So I'm a little afraid of how this is going to turn out, but we'll see. Okay, so what I want to do is two examples of change of basis. Because there's a question in the assignment about this, and altogether it's an important thing. We'll start by supposing that we have two different coordinate systems so two bases essentially for R2. So I have notes. The first one is, we are going to call it B. It consists of two vectors, U1 and U2. And those vectors are -1, 2, and 2, -1. Okay, and the second basis is the basis C. And this one consists of the vectors v1 and v2. And those vectors are 1, 0 and 1, 1. Okay? So what we want to do is, let's take a point in real space, let's say. And what point is that I want to look at? I believe it is 1, 5. So let's call x the point or vector 1, 5. So if you look at this basis B here, what you end up with is the following. So 1, 5 is a vector, it's 5, 1, 5, 1. 5 minus 1. Sorry. So 5 minus 1 is the vector that's 1, 2, 3, 4, 5, and minus 1. So I have this vector here. Okay. What is it in this basis B here? That basis is -1, 2. So -1 is this point here. 2 is 1, 2. This is U1. And U2 is 2 minus 1, so 2 this way, -1 this way. Okay, so what we want to do is express, for instance, x in this coordinate system B. I'm not going to go into the details. What you would do is you look for lines that are parallel to U2, lines that are parallel like this to U2, lines that are parallel to U1, and you check where this is. It turns out that vector in here has coordinates 1, 3. If I look at, we have colors. If I look at the other basis here, that basis VC, so vector 1, 1, is this one, which you can barely see, and vector 0, 1, 1, 0 is this one, and vector 1, 1 is this one. Okay, so now again I want to express this vector x in terms of these coordinate systems, and in that case I get that x in this basis C has coordinates 6, -1. And now the question that comes up in this context is, what is the change of basis matrix that allows me to express x in one of these bases as a function of where x is expressed before? Okay? So what we want to do is write u1 as a function of v1 and v2. Okay, so that means writing u1 as c1 v1 plus c2 v2. That is, so v1 is the vector 1, 0, so that's c1, 0, plus c2, c2. Okay, that's c1 plus c2, c2. And that equals the point minus 1, 2, or the vector minus 1, 2, if and only if c2 is equal to 2 and c1 is equal to minus 3. Okay, so now that means, let's write it another way, so that means u1 is equal to minus 3 v1 plus 2 v2. Okay, the same way we'll get that u2 is c1 v1 plus c2 v2, so this doesn't change. So this is c1 plus c2 and c2, and u2 is the vector 2 minus 1, and that's true if and only if c2 is minus 1 and c1 is 2 minus c2, so that's c1 equals 3. So that means that I can write u2 as 3 v1 minus v2. Okay, so just to store things away, let's put it here somewhere out of view. u1 is minus 3 v1 plus 2 v2, and u2 is 3 v1 minus v2. Okay? Now, if I want to express, so just a remark in passing, this is great, but I have to find out how to erase this in a meaningful way, because I will now zoom out the time for me to clean this, and then I will reappear once this is cleaned. Okay, so now recall that when we wrote x, the point 5 minus 1, in the coordinate system B, we had it written as, what was it, 1 and 3. This, like, it's in the coordinate system B, so this means that it's actually u1 plus 3 u2. Okay, I'm expressing this point as a linear combination of these two vectors, u1 and u2. So that is the expression for x in the basis B. But I have an expression for the coordinate vector u1 and u2 as a function of the coordinates v1 and v2. So if I use these expressions, what I get is, so I'm going to replace u1 by what I have computed, that's minus 3v1 plus 2v2, and u2 by 3v1 minus v2. Okay, these are the coordinates that we computed. So when I expand this, I get minus 3v1 plus 9v1, so it's 6v1, plus 2v2 minus 3v2, that's minus v2. So that's x in the coordinate system, the basis B. C, sorry, okay? You can see, and that was, if you turn back, well, I mean, if you go back a little bit, that was what we had started with. So what we have done here is changed the expression of x from being expressed in the basis B to being expressed in the basis C, okay? Now, you don't have to do this every time. It gets much easier because you can derive the change of basis matrix to do this operation every time by just applying to a vector. So to do this, remember that we saw the following theorem that told us the following. I'm caricaturing, okay? That if we have two bases, U1 to UN and V1 to Vn, then the matrix P, which has columns U1 expressed in the coordinates of the new basis C, UN in the new basis, this is the change of basis matrix. Okay, so this is the change of basis matrix. This pen is disappearing. Okay, how do we compute it? Well, we have this. Okay, I'm looking for the coordinates of U1 in the new basis and U2 in the new basis. And that's it. So my matrix P, that's going to take me into basis C from basis B, is simply the matrix that has columns -2, -3, 2, 3, -1. Okay? And when I apply this matrix to a vector, it gives me, so a vector that has coordinates. So if I take a vector that has coordinates in basis B, applying this matrix to it gives me a new vector in C. So you can see that to do this computation, all I need to do is compute this matrix, which means express the old basis vectors, U1 and U2, or U1 to UN, in the new basis vectors, and put these as the columns in my change of basis matrix, and what I get as a result is this matrix of change of basis. Okay, what I want to do now is to show you an example using a basis that is not what you're used to seeing. And this is going to be very useful in two of the exercises in assignment 6, I believe. So let me take two bases, and these are going to be bases of polynomials. Okay, so don't worry too much about it. I said at one point that vector spaces can consist of all sorts of things. Well, polynomials, functions, are a type of things we can put in a basis or in a vector space. Okay, so I'm going to take, oops, sorry, starting well. So I'm going to take a basis that's going to consist of three polynomials. 1 plus x squared, x plus x squared, and x squared. And I'm going to take a second basis, C, And that is what is actually called the canonical basis, the same way as for vectors 1, 0, 0, etc. make the canonical basis of Rn. This is the canonical base of the space of polynomials of degree 2. So 1x x squared. Okay, these are bases, and I will show you in a second that this is no more complicated than what we've seen elsewhere. Okay, and I'm going to take a point in this vector space. Okay, so this is the space, vector space of polynomials of degree less than or equal to 2. And we call this, we denote this vector space typically P2. A point in P2 is therefore any polynomial of degree less than or equal to 2. So I'm going to take a point here, and instead of writing it U, etc., like we do for the others, let's write it P of x. So P of x I'm going to take 1 plus x squared. So that's a quadratic. And it's an element in this space. I haven't made you show this, but you would easily show the same way as you've showed that the space of 2 by 2 matrices was a vector space. Well, you can easily show that this is a vector space. How do I express P of x in the basis B? It's very, very simple, and you will see that's why B is a basis. So if I think of P of x in basis B, how am I going to express it as an n element in this vector space with this basis? Well, I'm just going to write that it has to be C1 times this first element in the basis. And I'm going to write it by analogy with what we had before, but I'm going to indicate it's a function of x. C1 U1 of x. So this is what I'll call U1 of x, plus C2 times this, plus C3, U3 of x. So let me expand this. This is C1 times 1 plus x squared, plus C2 times x plus x squared, plus C3 x squared. And what I'm going to do now is I'm going to collect the coefficients of this point expressed in this new basis as a function of increasing degree polynomials. So I have a polynomial of degree 0, I just have C1 here. Polynomial of degree 1, I have C1 times x here, C2 times x here. And polynomial of degree 2, I have a C3x here, a C2x squared here, and a C1x squared here. So this is C1 plus C2 plus C3 x squared. But that equals this point, P of x, here, if and only if. So P of x in basis B is equal to C1 plus C2 x plus C1 plus C2 plus C3 x squared, if and only if. Well, C1, this coefficient of degree 0 has to be equal to 1. This coefficient of degree 1, there's none here. So C1 plus C2 is equal to 0. And the coefficient of degree 2 is 1. So C1 plus C2 plus C3 equals 1. So that's equivalent to saying C1 is equal to 1, C2 is equal to minus 1, And C3 is equal to 1 minus C2, which is plus 1, so that's 1 plus 1, 2, minus 1 is 1. So we can write, in terms of this basis, that the point P of x, polynomial P of x in the basis B, is given by this vector, 1 minus 1, 1. Okay? And I just need to multiply through these coefficients by these successive terms here to get 1 plus x squared. Okay, the same way we can express P of x in basis C. And that's going to be much easier, and that's why this is the canonical basis of P2, because remember that what we want is C1 times degree 0 plus C2 times x plus C3 times x squared. And that must equal 1 plus x squared. And that means that C1 is equal to 1, C2 is equal to 0, and C3 is equal to 1. So once you have the expression here in the canonical basis, you just have to take as coefficients the coefficients of the different entries. Okay? Now, how do I move from B to C? So let me show you this. So if you recall from the theorem, we saw that the matrix of change of basis that's going to take us from B into C is the matrix that has columns U1 in the new coordinates, U2 in the new coordinates, and U3 in the new coordinates. And my pen is dying again. So let's see if pink works better. Now, these U1, U2, U3, these are the vectors in this basis here. And as I just pointed out, it's very easy to express them in this coordinate system, because U1 in C is simply 1, 1, 1. U2 in C is there's no 0 degree polynomial, there's a 1, 1, and U3 in C is just 0, 0, 1. So the matrix of change of basis is equal to 1, 1, 1, 0, 1, 1, 0, 0, 1. And if you apply this to P1 as to P of x as we had represented it in the basis B, which was 1 minus 1, 1, if I recall, then if you multiply this matrix by this vector, you will find this guy here, 1, 0, 1. Okay, I'll let you check this.